All right, and we are good to go. So, June 9th, 2016, part 2. All right, so all we have left to do is a couple practice problems, basically. I have two two-dimensional ones and one three-dimensional one I want to work through. Okay. So for 2D problems, I'm generally not going to develop the whole unit vector. I'm generally not going to develop the whole vector. Rather, I like to do it using components of forces and perpendicular distances. So for 2D problems, oh, what just happened? Oh, all right, sorry. For two-dimensional problems, I recommend break forces into components, and use perpendicular distances. Use perpendicular distances. Because the moment can be found two ways. By A, doing the cross product, or B, multiplying a force by a perpendicular distance. Perpendicular distance. Also keep in mind, counterclockwise moments are positive, by definition. This comes out of the right-hand rule. So I don't know if hopefully I still have room here. I've put a lot of notes on here. Okay. Counterclockwise moments are positive. So let's see. Now let's look at this. So what do we have here? We have a 20-pound force is applied to the control rod AB as shown. Knowing that the length of the rod is 9 inches and that the moment of the force about B is 120 pound-inches clockwise, determine the value of alpha. So I'm going to do this using the method of perpendicular distances. So first I'm going to look at the geometry. I know this is 9 inches. I know this is 9 inches. I know this is 9 cosine 65. And the 9 inches just was given to me. And this is here 9 sine 65. Oh my god, that looks awful. That's what I get for trying to write sideways. Okay, 9 sine 65 in the clearest writing imaginable. Okay. So now let's look at the forces. And actually, you know what? In fact, first I'm going to extract this out and actually get the values of those distances as a decimal. Okay, so I'm going to have my force triangle. Actually, let me draw this a little bit bigger. I think it'd be better if I'll just write over the prompt a bit. Or maybe I'll actually write it down there. So I'm going to have this triangle here. This is 9 cosine 65 is 3.804. and we're interested in the moment about B, then 9 sine 65 is 8.157. Is 8.157 inches, and the hypotenuse, of course, is 9 inches. Now, if we look at the components of the force on here, I'm going to have Fx and Fy. Now I know Fx is going to be, since the overall force here is 20 pounds, Fx is going to be 20 sine alpha. And Fy is going to be equal, oh, derp, I'm an idiot again. Mixing up my sines and cosines. 20 cosine alpha, sorry. And Fy is 20 sine alpha. 20 sine alpha. Any questions on that so far? So far we actually haven't done any moment calculation. Mm-hmm. Yes, the 20 is given. Okay, so what's next? Well, now we just apply balance of moments. So I know that the sum of moments about point B is 0. So notice my notation here. Sigma means sum, moment, M for moment, B is the point that I'm taking moments about, and then I have a little symbol here showing counterclockwise positive. So again, M for moments, sigma for sum, B for the point I'm taking moments about. If I was taking moments about here, I'd have point A. So I'd have M sub A, etc. But
that's the positive to remind you at the end that's positive.
That's just to remind me that counterclockwise is positive, basically.
On like an exam, sorry, do you need the symbol like that?
Do we need this on an exam? Be helpful, but that is probably most proper notation. Now, let's see. So again, I'm going to use the method of perpendicular distances. The method of perpendicular distances says that the moment generated by a force about a point is equal to the magnitude of the force times the perpendicular distance to its line of action. See, look at this. This force has a line of action here. The perpendicular distance is 8.157 inches. So the perpendicular distance from B to Fx's line of action is 8.157 inches. So this is Fx times 8.157 inches. Fx times 8.157 inches. Now, now I do need to do one thing, and that is I need to make this negative. I need to apply a negative here because it's generating a clockwise moment about point B. A counterclockwise moment is positive, a clockwise moment is negative. So counterclockwise positive, clockwise negative. Plus Fy, the y component of the force, times its perpendicular distance, 3.804. This is the perpendicular distance from the line of action of Fy to point B. Again, I'm not actually trying to look at the, you might be tempted to say, oh, force times distance, 20 sine theta times 9 inches. That's not what you want to do, because it's not the actual distance from the point the force is applied to the point we're taking moments about. It is the distance from the it is the perpendicular distance from the force's line of action to the point we're taking moments about. So there we have it, and that is, let's see. Oh, actually, you know what? I lied here. How did I lie?
It's not negative.
It's not 0. It's 120. That would make the math simpler if it was 0, but it's not. I lied. And all of this equals, however, it's going to equal negative 120 because it's clockwise. Negative 120 pound inches.
I don't understand the clockwise and counterclockwise. How are you looking at that and determining clockwise?
Okay, good question. How do we determine clockwise or counterclockwise? See, look here. The Fx, it wants to rotate like this around point B. Fy wants to orbit like this about point B.
Okay.
Clockwise, counterclockwise. Clockwise and counterclockwise. Okay, so now the math gets fun. So now we just say, all right, negative Fx, and I just plug in negative 20 cosine alpha times 8.157 inches plus 20 sine alpha times 3.804 inches equals negative 120. And now we could solve this any number of ways. I'd probably solve it graphically if I have a graphing calculator handy. Negative 20 times 8.157. So negative 163.1 cosine of alpha plus 20 times 3.804, 76.07, 071 sine alpha equals negative 120. We could solve this through trig methods, etc., etc. I'm just going to be lazy and use my calculator. So I'm just going to plug this in and see what I get. I'm just going to solve by graphing really quickly here. Let's see, cosine of x, and then copy that, plus times the sine of x equals negative 120. Get the right zoom window. Let's say negative 0 to 90, from negative 200 to 200, and graph it. Oh, I need to actually have lower bound, upper bound. I get that alpha equals 23.2 degrees. If I didn't have access to a graphing calculator, I would use trig properties. Okay, so questions on that?
Tell me again why y is positive. You look at that force diagram and you see y going.
I see y going down. Are you okay with that y is going down? So okay, so the question is again, show me again why Fy is positive. Why the moment generated by Fy is positive. And the reason for that is, okay, are you okay that Fy is going downward, right? You okay with that?
Yes.
Okay. And so you look at this and say, this is clearly causing a counterclockwise rotation about point B. Fy clearly wants to rotate counterclockwise about point B. Imagine for a moment that you can kind of think of it this way. Imagine that I just had nothing but Fy on here, okay? And I had a rod here and a pivot here, okay? Which direction would this thing turn? That's one way to visualize it. Imagine I were to come here, attach a rigid rod to a pivot point here, and then applied a force to this thing. This thing would, which way would this rotate? And that's how you determine that. This thing would clearly rotate in a counterclockwise direction. So therefore, the moment generated by this is positive. Now, it's very easy to get trapped into the thought thinking, oh, the force is downward, the force is negative, therefore the moment's negative. No, it's not. The sign on the force has nothing to do with the sign on the moment. It has everything to do with how it is oriented in relation to the axis of rotation. So, or the point of rotation. So a positive force can generate a negative moment, a positive force can generate a positive moment, a negative force can generate a positive moment, etc. You have to actually look at it and ask yourself, which direction is this thing going to rotate? Okay, does that kind of clear that up? Okay.
So you're applying Fy separately of Fx.
Exactly, I'm applying Fy separately of Fx, yes.
I was trying to apply them at the same time.
Ah, yeah, if you try to apply them at the same time, it's not going to work so well. How did I jump from here to here? I solved by graphing. Alternately, you can use trig methods. I just didn't feel like going through all that right now. Okay, all right. Moving on. Okay. Here we have a classic problem. We're not actually, it might look like we're trying to pull a stump, but we're not. We're actually using the stump as a base. It is known that a force with a moment of 960 Newton meters, about D, is required to straighten the fence post CD. If D is 2.8 meters, or if D equals 2.80 meters, determine the tension that must be developed in the cable of winch puller AB to create the required moment about point D. So we have some rancher out in West Texas somewhere who has a fence and the fence is crooked and wants to straighten the fence. And I don't know exactly how he knows this, but somehow said rancher knows that it will require a moment of precisely 960 Newton meters to righten that post. And so he needs to figure out which of his many winches to use. So he needs to, and for some reason they're all rated, well, each of them is rated by pulling force. So he needs to know exactly how much tension he's going to need before he selects the appropriate winch, and then he can go out and righten the post. And he prefers to do this using the principles of statics instead of just trying it and finding out. He could just use his largest one and see if that worked. Well, maybe that might work. That might be too much. It might actually break the pole, but he could just eyeball it. But no, he's a former engineer, and he decided to take up ranching, and now he insists on doing everything with math. So, and that is the contrived example. So we know that D is 2.8 meters. We know that D is 2.80 meters. And we know that there is a force here. There is a force here, a tension force, T. And that's what we're trying to solve for. And this will generate a moment here, MD, that looks awful. MD is going to be equal to 960 Newton meters. Equal to 960 Newton meters. However, this has both a Ty, so in some respect it's similar to the other one, a little bit, and the Tx. Okay, first I need to analyze the tension force here and somehow tease out the, we don't have angles, instead we have dimensions, so I need to tease out the x and the y components. So let's look at the tension here. What do I have? The triangle, the dimension triangle for this thing here I'm going to have this looks to me like from here to here in the x direction is 3.0 meters. This comes from the 2.8 meters to the point D plus the additional 0.2 meters the horizontal distance here. And then this is 0.875 meters. Then I want to find this hypotenuse, so I'm just going to use my old friend, the Pythagorean Theorem. 3 squared plus 0.875 squared, and I get 3.125 meters. Okay, 3.125 meters. And I know that this will be proportional to my force triangle. This will be proportional to my Tx, Ty, and T. So Tx, I'm not going to worry about the positive negatives on these because I'm just going to take the, I'm just going to eyeball it anyway to figure out whether they're going positive or negative moments. So Tx is going to be T times 3 over 3.125, or which is equal to 0.96 T. Ty is going to be equal to T times 0.875 over 3.125 equals 0.875 over 3.125 is 0.28 T. 0.28 T. So questions so far? All I'm doing so far is applying principles of, all I'm doing so far is finding the x and y components of the tension. Now I can do a balance of moments. So let's look at this triangle here. Again, I'm going to do this using the perpendicular distance method. So this is 0.2 meters. This is 0.875 meters. And I'll again need to use the the Pythagorean theorem. Plus 0.875 squared. And I get 0.898 meters. 0.898 meters for the hypotenuse. So, although actually, you know what? I probably won't even need that. I don't know why I calculated that, but we have it if we need it, which we won't. Okay, so basically here, this is point D, and this is point C. And I have Tx and Ty with their corresponding perpendicular distances. So the sum of moments of these forces about point D, counterclockwise positive, is going to be equal to 960 Newton meters, which is going to be equal to Tx times, let's see. So I don't actually want to multiply by anything with hypotenuse. I'm going to multiply by its perpendicular distance, which is 0.875 meters. Again, so Tx has a perpendicular distance of 0.875 meters from point D. Its line of action, perpendicular distance. And it's positive because it's causing a counterclockwise rotation about point D. Minus Ty times 0.2 meters. Okay. Questions? Any questions so far?
What's point D again?
Point D is the point at the bottom of the post. It's the point that I'm summing moments about. That's the point that I want the moment about to be 960 Newton meters. All right, and now it's just, and the rest is just math.
Where did the point 2 come from?
The point 2 right here. Yeah, it's the perpendicular distance from Ty to point D. Okay, so 960 Newton meters equals point Tx, which is 0.96 T. The ultimate goal here is I'm trying to find T. So 0.96 T times 0.875 meters minus 0.28 T times 0.2 meters. All right, then I'm going to combine all this stuff together. 0.96 times 0.875 minus 0.28 times 0.2. I get 960 Newton meters equals 0.96 times 1 minus 0.28 times 0.2. I get equals 0.784 T, 0.784 meters T, I should say. And then T, simply by dividing, is equal to 1,224 newtons. Just like so. So, questions on that?
All distances are positive?
All distances are positive?
Yeah.
Okay, so in this case, I don't need to worry about putting a positive or negative sign on the distance because I'm looking at this and actually applying a positive or negative to the entire moment. That's when you're doing this. If you're doing actually finding the vectors directly and doing cross products, then you'll need to worry about that. But for this, for simple 2D systems, I prefer just to eyeball it and say, okay, this one's positive, this one's negative. You'll find that often it's a lot simpler. All right, but we do have one example. Our final example here today will be a actual full-length three-dimensional one, finding full vectors, etc., etc. And the homework problems I put up are a mixture of these. All right, other questions?
So it takes 1,224 newtons to move the pole 0.2 meters, but somehow he already knew the moment.
No, that won't cause. So the question is, it somehow takes 1,200 etc. newtons to move it to 0.2 meters. Well, it's actually not going to move that. The base isn't going to move at all. It's going to rotate. Can you?
Rotate it.
It's going to rotate and upward and rotate and right it essentially. Anyway, so there's that. Other questions? Yes. Shouldn't both the tension forces be counterclockwise? We are breaking them apart into two different forces. That's what you need to be considering. We're breaking them apart into two different forces. This one, Ty, is causing it to rotate clockwise. Look at this force here. It's causing a clockwise rotation. See? This force is clearly rotating clockwise about point D. Think about it. It's true. Tx is causing a counterclockwise rotation. That's why it's positive. Ty is causing a. Okay, I think the trouble you're having is that you're not visualizing them as broken apart forces. You need to think of them as completely separate and independent forces because they are. So, the components of forces are independent. Don't try to look at them together. Consider them independently. All right, other questions? Okay, moving along. Ooh, we got an angle iron. All right, I'm going to do just one of these. I think I'll just do part. I think I'll just do part B on here, just for illustration purposes. Okay, so we have wire AE is stretched between corners A and E. of this bent plate. Knowing that the tension in the wire is 435 newtons, determine the moment about O of the force exerted by the wire on corner E. So I'm going to draw a few vectors. First, I'm going to have ROE. Row. Then I'm going to have FEA. So our final result will be the moment about O is equal to ROE cross FEA. So then the rest of this is just setting this up. So we need to find the moment generated by this force about point O. I need the vector from O to E, because that's some point on the line. I could also use the vector here, but I think this will be a little simpler. Crossed into the force vector of the tension at point E. So we're going to need to find each of these. So let's just get cracking. So a lot of this is going to be a repeat of stuff we've seen before, but that's okay. So you know what? First, let's knock out ROE. It's going to be fairly straightforward. ROE is going to be, the first component is going to be positive 120, 120I, plus 0J, plus 120K. Because it's 120 millimeters in the Z direction. Now, I'd like to get the vector for line EA, because we're going to need to get the unit vector for it after that. EA. All right, let's think about this. It's going to be negative 210I, because from here to here, we lose 120 millimeters in the, we lose 210 millimeters in the x direction. Plus 160J. I'm kind of leaving out the units here because I'm lazy. Plus 160J minus 120K. Questions on any of this, how I've gotten this? It should be, because look from here, to the back of the plate, it's, we start at the coordinate of E is positive 120. Here it's 0 in the Z. So we lose 120 Z units in the Z direction. Z. X, Y, Z. We go up in the Y, we go to the left in the X, and we decrease in the Z, going from E to A. Next, we can find lambda EA, which is going to be equal to negative 120, or I keep wanting to say 120, it's 210. Negative 210I plus 160J minus 120K, all divided by the square root of, so just the Pythagorean here, 210 squared plus 160 squared plus 120 squared. Okay, and let me throw that in my calculator to get a unit vector. comma 160, comma negative 120. Square root of 210 squared plus 160 squared plus 120 squared. This divided by this. Okay, 210, 160, 120. And I'm getting that a unit vector of negative 0.724i plus 0.552j minus 0.414k. Questions on that? Again, I'm just finding the unit vector. I'm just finding the overall vector along the forces line of action. Then I'm finding the unit vector of that vector. Next, I want to find FEA. And this is simply 435 newtons times negative 0.724, 0.552, comma, negative 0.414. So I just multiply this by 435 as a scalar multiplier. And I get, hey, look at that. It's like it's a book problem or something. Comes out to an exact number. FEA equals negative 350 or 315 newtons I plus 240 newtons J minus 180 newtons K. Okay? Okay. That pun fell very, very flat. All right. Yes.
Kind of stupid about, but this is about notation. EA is the same as REA, right?
Yeah, you could call that R. The question was, EA is the same as REA. Yes, you could call this REA very simple, very simply. It's all arbitrary. So yes.
How did you get negative 210i again?
The question is, how did we get negative 210i? Look from here to here. What is the x coordinate of this point? What is the x coordinate of this point? Positive 120. The x coordinate of this point is positive 120. The x coordinate of this point is negative 90. So going from here to here, we fall back 210 millimeters in the x direction. Okay? So that's where the negative 100, where the negative 210 comes from. I know when you're looking at three-dimensional problems, it's hard to wrap your brain around initially. It takes some getting used to. All right. Especially if you haven't taken. Have you all taken your engineering graphics class?
Fun class.
Huh?
It's a fun class.
It is fun if you have the right professor, yeah. But especially if you haven't taken your drafting class, your engineering graphics class, that can be a bit difficult to imagine for some students. Anyway, so we have FEA, we have this, we have this. All we have to do is take the cross product, and we are done. So let me put this aside. Let me create a little space here. So I want ROE and FEA and I, J, and K. All right, so I'm going to have 210, 0. That's going to simplify things a lot. Huh? That's fine, 120.
You said 210, you were 120.
This is 120.
No, when you were writing it, you said 210.
Oh, when I was writing it, I said 210? Okay, whatever. Well, I wrote it right. That's what matters, right? Something like that. Okay, 120, 0, 120. I can tell I'm ready for the weekend. Negative 315, 240, and negative 180. Okay, so let us find the cross product. Need a little more room here. Okay, so I'm going to use this. I'm trying to squeeze all this in one slide. The moment, O, is going to be for the I, well, 0 for this one, minus, so basically negative 240 times 120, I, minus 120 times negative 180, minus negative 315 times 120, J, plus, basically this term will be 0, so just 120 times 240, K, like so. So negative 240 times 110, negative 240, where were we? Negative 240, because it's subtracted. Wait, did I screw that up? Possibly. Yeah, okay, thank you. Okay. It's possible, as we've known, I'm not infallible, contrary to popular opinion. So here, negative 28800. You know what? I'm just going to divide these all by 1,000. Is that okay? That'll allow me to go to Newton meters instead of Newton millimeters. As I go with this, I'm just going to divide all these by 1,000. So this is going to be negative 28.8 Newton meter I. Okay, so now 120 times negative 180 plus 315 times 120. All that times negative 1. So 120 times negative 180 plus 315 times 120 divided by 1,000. And this is minus 16.2 Newton meter J. And then 120 times 240 is divided by 1,000 again, plus 28.8 Newton meter K. And that is our moment vector. So this is actually a vector. That's why the cross product, again, is sometimes referred to as the vector product, because the result is the vector. Later on is a vector. Later on, we will be learning about something called what's sometimes referred to as a scalar product or the dot product, which you have seen before. Yes.
So conceptually, the moment vector expresses the axis of rotation.
Yes. The question is the question was conceptually does a moment vector express the axis of rotation? Yes, and it basically says this thing will experience a tendency to rotate about different axes. Okay? All right, other questions? Okay, so I think that should do it for today. If you have any questions, I will be available in my office hours. Please be mindful of the calendar. There's an exam coming up next week, so do be aware of that. Oh, yes. Question? Okay. Yeah, so I do have office hours today. Feel free to drop by or send me an email if you need any help. Send me an email over the weekend. I should be reasonably available. You have the homework problems. I will post some solutions for the ones we've already done. That should do it. I'll see you on Monday. And as always, thank you.
If you have any questions, we send it through YouTube.